instructions yesterday, but I don't always follow his fine direction. Let's go around the room, virtual room, and see who is here. And this gives me a chance also to try my hand again at pronouncing everyone's name. So I know most of you are here. Let me start as follows. Sivanan Devarakonda. Are you here?
I'm here.
Fantastic. Davida Di Nabila. Are you here? Maybe not.
Davide is
Jan,
not here.
Okay, Jan Dries.
Yes, I'm here.
Great. Boss Groot Nibbelink. Groot Nibbelink. How am I doing on that?
Yeah, that's pretty good.
Well, it's not too bad, right? Give me the correct pronunciation.
Groot Nibbelink.
Okay, I'll work on that. James Hardy. Okay. Ricky Hollenbach.
I am here.
Good. Anil Mohan.
Yep, I'm here.
Danielle Vasila. Vasila.
I'm here.
Give me the correct pronunciation.
Vasselli.
Vasily. Is that right?
Oh yeah,
That's close. Okay. Yeah. And finally, Yuhan Wang.
Yeah, I'm here. Good morning, Professor.
Okay, great. And Michael Lee is here, most importantly, because he's going to keep me on the straight and narrow.
I am indeed.
Well, yeah. Now, let's go around the room one more time in the same order. I should have asked you this the first time. I'd like to know where you are physically. So I'll move backwards. Yuhan Wang, where are you physically at the moment, geographically?
It's me here. Can you see me? I'm speaking.
Okay. All right. Daniela Vasily?
I'm in Durham, North Carolina at the moment.
Okay. Anil Mohan?
Durham?
Yeah. Ricky Hollenbach?
I'm currently in Durham, but I might be splitting some time in Philadelphia, Pennsylvania as well.
Okay. Let's see. James Hardy? He wasn't here, right? Is that right? Okay. James Hardy. And Boss Groot
Yeah,
Nibbelink.
I'm in Durham still.
You're in Durham. Jan Dries?
Yeah, I'm in Durham as well, but I might leave soon.
You might be where?
I might leave soon to Belgium, back to Belgium.
Oh, back to Belgium. Okay.
Dr. Dell, James Hardy has just joined us.
Hey, James. Great. Hello, James. Where are you physically?
He is still connecting his audio.
Oh, okay.
He is looking. There he is. Perhaps.
I'm sorry?
Matt, we can hear you.
James Hardy. You're in Durham?
I'm in Kentucky right now.
Oh, you're in Kentucky. That's right.
Yeah.
Okay.
I'm over top the Appalachia.
How's everything in Kentucky?
It's a little bit cold. It's supposed to rain for the next few days, but everything's okay. Everything's good.
Okay. Okay, that's good to know.
Yes,
David Di Nubula. He wasn't here, right?
Davide is not here.
Davida?
Yeah, he's not here.
Okay, he's not here. And Sivanan, where are you?
I'm here in Durham as well.
Okay, fine. So we're online, but we're not too far removed from each other. Well, we're going to make the best of this situation, and we're going to all learn a lot, including me, probably as much as anyone, if not more. So in terms of this procedure, the good news is I have my book online, as you see. And so I think I had asked you to read pages 161 to 191, okay? And I know you've missed homework desperately. You've been chomping at the bit to have more homework. So let me say two things about that. First of all, with respect to the most recent homework that you had submitted, Michael Lee and I are going to get together this afternoon and find a way to get that back to you, at least electronically, if not otherwise. And so we'll probably discuss that at our class meeting on Thursday. But in the meantime, I'm sure you'll want to start working on the next homework assignment. And so the next homework assignment is to find all of the typos, all the typographical errors in pages 161 to 191 in the book. And I've identified about a half a dozen, which I will not tell you about yet. And you may find those and even more. So that will be very helpful to me and hopefully a learning experience for you. Now, before we launch into chapter 4, which is all about unsteady aerodynamics, let me pause and see if there's some questions. And let me preface that by saying that I think this is going to work better if you ask lots of questions, either live, as we are now, or by email. And any question you have is a good question by definition, and I'll try my best, perhaps working with you collectively, to come up with some good answers. So are there any questions at the moment? And don't be shy, because I can't see you raise your hands. At least I don't think I can. No, I can't. So are there any questions about life, what we're going to do about no basketball, the rest of this course, whatever? Any questions? I hear a resounding silence. Okay, well, I hope that, yes.
So you got any idea when exactly we're gonna have the oral exam?
Well, that's a good question. I hadn't really gotten that far in my thinking. I don't see that we're going to be able to, because I don't think we're going to be back on campus by the end of the semester. But of course, that begs the question of when is the end of the semester? As you know, the university decided to have a 2-week spring break rather than a 1 week. But even if you extend out the semester an additional week, I think that only takes us up to no further than beyond the end of April. So I don't see how we're going to have an oral exam face to face, but maybe by Skype or some means, we probably could have an oral exam one-on-one. Yes, as I'm thinking about it. So let me look into that, because I think that would be a good thing to do. It'd be nice to see each other's face and have an exam. I know you wouldn't want to miss that experience, but thank you for asking that question.
Thank you.
You're welcome. I hope you're not sorry you asked that question. I think it would be a good thing. I have participated in sort of 2.5 final public oral exams in the last week. One was Michael Lee, who did very well on his. Another was Matt Tedesco, who did a nice job yesterday. And then I heard a portion of yet another one just to see how it was going. It was not in my area, not a topic I knew a great deal about. And those final public orals worked out well. We used Zoom, okay? And we had, I think, a good discussion. So that's possible. And we might use Zoom. I suppose we could use Zoom one-on-one. No reason not to. Is that right, Michael?
Yes, indeed.
Okay, great. Okay, other questions? That was a good question.
Would homework 8 be due a week from today?
Yes.
Perfect.
So just send me an email identifying any typos you found in those 30 pages, 161 to 191, by a week from today. Other questions? Okay. Well, if
I'm sorry, Professor. It's Michael.
Yeah, that's fine. Sure.
So logistics for the homework submission. I'll also have a link up in Sakai pretty soon, and you'll be able to submit there.
Okay, great. Thank you. Thank you. Anything else before we launch into chapter 4? Okay, so today, and particularly since this is our first time back, what I thought I would do is I will try to give you an overview of what's in Chapter 4, not just in those 30 pages that you're reading at the moment, but beyond that as well. And so you'll have a big picture of what we're trying to cover the rest of the semester. And most of the rest of the semester will be Chapter 4. So the way Chapter 4 works is as follows. We start off with a derivation of the fluid equations of motion. So let me go down a bit here. Oh, I see. Michael told me how to get to the right page, I think. 174.
Not quite there. Over, if you go over to the left.
To the left.
Yeah. So you see it says 4/294. Move your cursor up. Yeah, right there. 190.
Right here. Thank you.
Mm-hmm.
Very good.
And if you hit enter.
Oh, that's right. Hit enter. Thank you.
You'll have to scroll just a little bit.
I must have typed in the wrong number.
Remember, the page number doesn't connect with the.
Oh, that's right. I hit it. Typed in 191, didn't I?
Yeah.
Thank you.
Mm-hmm.
Yeah, I was off by 20. Okay.
There it is.
Getting close. Okay. So here's started Chapter 4. And the first part of it derives the fluid equations of motion. Now, I'm assuming that most of you, if not all of you, have taken at least one course in fluid mechanics. And depending on the course you took, they may have derived the equations for time-dependent flows, or they may have derived equations for steady flows. But of course, we want time-dependent flows because we're interested in flows about bodies that are moving, oscillating wings, and so forth. And so at the very start, we have to decide at what level we're going to model the fluid. And one major division is, are we going to do viscous flows or inviscid flows, that is non-viscous flows? And this chapter is entirely devoted to inviscid or non-viscous flows. So we're dealing with what is usually called the Euler equations. The equations of fluid mechanics tend to be named after famous people. Actually, that's true in a lot of the solid mechanics literature as well. But the Euler equations are the equations of fluid mechanics for inviscid flow. And I'm assuming that most of you have had occasion to see a derivation of those. You can do it several different ways, but usually the way to do it is you look at a control volume of fluid and you say things like the increase in the mass inside the control volume is equal to the mass coming in minus the mass coming out, and that's continuity of mass. And then you have another statement that's basically Newton's second law that says the forces on the volume, which are the pressure forces on the area enclosing the volume, must be balanced by the time rate of change of momentum. That's Newton's second law. And that then has to be augmented by some thermodynamics, which is usually an equation of state, which in our case is going to be isentropic flow, which means that there's a certain relationship between pressure and density. So my first question to the class, and I see I can ask you questions too, is have all of you seen a derivation of the fluid equations of motion for an inviscid fluid? Or conversely, if you haven't, and if you haven't, that's okay. That doesn't mean you're a bad person or in any way not to be appreciated. But has anyone not had occasion to see a derivation of the fluid equations of motion? Hearing none, then I will simply ask you to review the pages starting with 171 up to 176, and you'll see the equations of motion. For example, equation 4.1.8 is that famous Newton's second law for that volume of fluid. 4.1.9 is the equation of state that comes from thermodynamics that gives you a unique relationship between pressure and density. And then this bracketed term in equation 4.1.8 is essentially the equation of conservation of mass. It's the time rate of change of density, and then there's a convection term because there's fluid going in and out of that control volume. So that when that bracketed term is 0, that's the conservation of mass. And so we can set this term equal to 0 in Newton's second law, which obviously simplifies that equation. Okay, so what do we have? We have some unknowns. We don't know the density, at least not initially. We don't know the pressure, although if we know the density, we can find the pressure from this equation very readily. And of course, we don't know the vector fluid velocity, which is q bar. Never, ever to be confused with the dynamic pressure, right? So we have these unknowns, pressure, density, and the velocity vector. And happily, we have just the right number of equations, which if we can solve them, will determine those quantities. So we have a scalar equation, this equation of state. We have another scalar equation, that's this conservation of mass, bracketed term set to 0. And then, of course, Newton's second law itself is a vector equation. So we have two scalar equations, one vector equation, and we have two scalar unknowns, pressure and density, and one vector unknown, namely the fluid velocity. The reason this is challenging to consider is that all of these equations and unknowns are coupled. So we can't solve these equations one at a time. We have to solve them together. Although, obviously, we can take this equation and everywhere we see density, we can replace it by something involving pressure or vice versa, since this is a simple algebraic equation. But in general, we've got some nonlinear partial difference equations that are going to be hard to solve. People today solve these equations. In fact, they even solve the viscous counterpart, the Navier-Stokes equation, using numerical methods. And for the most part, we don't treat those in this course because Professor Howell, that's H-O-W-L-E, Howell, talks about that in his course, how to solve these equations numerically using a finite difference, finite volume, finite element, finite something approach. There are other finite element courses at Duke that also look at fluids as well as solids. And I think to some degree, Professor Hall, H-A-L-L, talks about that in his course on nonlinear dynamics. But we're going to take a different approach. And the basic idea is something called small perturbation theory. And the thought is we have some mean flow, which in the classical theory is just a constant velocity at which this wing is moving through the fluid. And we're going to assume that when the wing moves, the motion is small enough that the perturbations to the fluid are small, hence small perturbation theory. And then we can simplify these nonlinear equations and construct a linear model. And we like linear models because then we can do flutter analysis and cusp response and all that. To get from this set of equations to a simpler equation, which will turn out to be the wave equation, we need to go through a couple of steps. So let's see. Oh, okay, one thing we'll need to do, and that's done in this section 4.1.3, is we'll need to, we're going to eventually find an equation which will allow us to determine q bar, the velocity vector. But if we know that, then we can solve this equation for the pressure, and that's done in this section. And that was done using a theorem due to Kelvin and basically done by one of the Bernoullis. There were 3 Bernoullis, I think a father and 2 sons. I forgot which Bernoulli did this, but this is called Bernoulli's equation, the relationship that tells you what the pressure is given the velocity. And eventually, with a little bit of algebra, you get to first of all, Kelvin's theorem says that if the flow is irrotational, namely that the curl of the velocity vector is a constant, and you can set that constant to 0 because it is 0 far away from the airfoil, then Q bar itself is the gradient of a potential. And hence, this approach is usually called potential flow theory. So we're going to think of Q bar as being the gradient of a potential, the velocity potential. And using that for Q, then we can eventually obtain Bernoulli's equation, which is equation 4.1.15. And so, and then we can also determine this function of time by looking at the boundary conditions far away from the wing is essentially a constant given by this equation. It's the mean velocity squared divided by 2. So it really isn't a function of time, although mathematically it could have been, but it turns out using the conditions at infinity far from the wing, it's really not, it's just a constant. So here's the useful form of Bernoulli's equation. And then we have to use this relationship we had from the state equation between pressure and density to evaluate this integral. So the utility of Bernoulli's equation is if we can ever determine phi, the velocity potential, we can then determine P. And note that this equation itself is nonlinear because here's a product of gradient of the potential. But we can linearize this too if the motion of the airfoil is small and therefore the perturbations to the flow are small enough. So moving right along, we've done this in only 8 pages. It's really quick, right? But then the next thing you need to do is you need to derive a single equation for the velocity potential. And here's where we explicitly use the idea of a perturbation. So this is the continuity or the conservation of mass equation rewritten in a slightly different form. We can evaluate some of these terms using something called Leibniz rule in our equation of state. And if we keep going, eventually we obtain not quite, but almost a single equation for the velocity potential, and that's this equation. Now, we've not yet assumed small perturbations. We've just plugged ahead without making that assumption as yet. And you'll see that this equation has some virtues. It's a single equation for a single unknown, namely velocity potential. And once we have the velocity potential, then we can evaluate the pressure, which is the practical thing we usually want to know. But this equation as it stands, without further manipulation, is a nonlinear equation, right? Here's some nonlinear terms here. There's a cubic term because it involves 3 powers of the gradient of phi. Here's a quadratic term. This is a linear term. This is a linear term. Actually, even this is not a linear term because this A is the speed of sound, which we need to talk about. And it itself depends on phi in the full nonlinear theory. Okay, so now I'm going to pause. I've given you a guided tour of the first 10 equations, the first 10 pages or so of this chapter. My question to you now is, given that guided tour, and now you know what you're looking for, can you, if you have not already read these 10 pages, can you read them and understand how this equation was derived? And the answer should be what? Yes, right? Hello, are you still there?
Yes.
Okay. Do you need me to say more about what I've just said? Do you have any questions about what I've just said?
Can this equation be applied as it stands to all 3 dimensions if you wanted to?
In 3 dimensions, absolutely. Because this is written in terms of the gradient operator, right? So we just need to make sure that we have the gradient operator in 3 dimensions if we are in 3 dimensions, or if we're only in 2, we could use it in 2 dimensions. But yes, this is fully 3-dimensional as far as spatial matters are concerned. Absolutely. Okay. In fact, the first, let's see, when would this been? In the 1970s, so 40 some years ago, at the dawn of the computer revolution, when people first started talking about computational fluid dynamics, which is a phrase you've probably heard from time to time. Now, when people talk about computational fluid dynamics, they usually think of solving the Euler equations, not the potential flow equations, but the Euler equations in their original form, or the Navier-Stokes equations. But the first computer solutions to the fluid equations were largely using this equation. It's a nonlinear PDE, right? A nonlinear partial difference equation. But it is assuming this irrotationality. What does that mean? If you look very closely, well, first of all, we've neglected viscosity, of course. But beyond that, if you assume the flow is irrotational, that says if there are shocks, which there will be as you get up to the higher flow velocities, Mach numbers in the neighborhood of 1 and beyond, if there are shocks, they have to be weak. And we'll have to discuss what that means to be weak. But it turns out this equation does give you a decent answer for a lot of flows around sufficiently slender bodies which are moving with sufficiently small motion. Okay. Yeah. Does that help?
Yes, it does. Thank you.
Okay. Other questions? Okay. Okay. So now, this is not the whole story, and that's because this A, the speed of sound, itself is related to C, and by manipulating Bernoulli's equation, remember Bernoulli's equation, we can write down another equation that relates A and B. So the true full nonlinear theory involves this equation plus one more. And let's see if I can find that one. First of all, I'll define the speed of sound. That's this equation. By the way, can you see my cursor? Hello? Okay, great. Okay, so this is the definition of the speed of sound squared. It's the derivative of the pressure with respect to density. Now, why do we find it that way? Because if you do a little bit more analysis, you can interpret this derivative of the pressure with respect to density as the speed at which local disturbances in the fluid are propagating, right? So if I drop the proverbial pebble in the pond, or maybe I use a firecracker in air, I disturb the system in some way, the fluid system, then that disturbance will move away from that point of disturbance in all directions with a certain characteristic velocity. It's not the fluid velocity, it's the propagation velocity of the disturbance. And that's what A is. It's the speed of sound. They call it the speed of sound because in air we're thinking of a pressure pulse hitting our ear that we can hear. So this is the speed at which the disturbances are moving. And it's related to this derivative of the pressure with respect to density. So with that definition, that means, for example, I can replace pressure or density in terms of speed of sound using that relationship. And moving right along, here's our friend, the equation of state. Well, using this equation of state, I can compute this derivative, okay? And I can put that in, and therefore I can compute A squared. What about this? First of all, A infinity is the speed of sound very far from the wing, right? Where the flow is presumably vice versa. And then, of course, we have the velocity potential. It turns out that if the disturbances are small enough, that gradient phi dot gradient phi is essentially equal to u infinity squared. And if I'm far from the airfoil, phi is essentially is a constant, and therefore this term is also zero. So far from the airfoil, the right-hand side, as you would expect, should be zero, and therefore A should be equal to A infinity squared. Okay? In the classical theory of small disturbances, we essentially assume that the right-hand side is nearly zero, and we'll show how that works in a moment. And therefore, we replace A by its value at infinity, okay? So in the classical theory, A is a constant, equal to the speed of sound, essentially when the wing isn't there, right? So that means then, if I go back up, in this equation, A is, in the small disturbance theory, this is going to be a constant, okay? Then, I'm essentially going to ignore almost all of the nonlinear terms, right? Here's a nonlinear term, and here's a nonlinear term. And therefore, this is the Laplacian operating on phi minus 1 over a constant now, a constant speed of sound, times the second time derivative of phi. And therefore, that equation, you will say, that's one of the ones they told me about in my course on PDE, and it is the, which equation? It's what equation? You're supposed to remember the, I'm sorry?
Students, you can chime in here if you want.
Absolutely. Please chime in. What equation is this, anyone who feels brave enough to say? Well,
I think we might have a connectivity issue, Dr. Dowell. Give me just a second. Can anyone check in with their microphone and let us know they're still with us?
Can you hear me?
Yes.
Yeah, it worked for like, I mean, at least on our side, Bas and I were disconnected for like the past 2 minutes. So I think it might be on our side.
Okay, mine restarted, but I only lost about 10 seconds, so I didn't want to.
Yeah,
I didn't want to make a thing of it.
Our Zoom had to restart as well.
Okay, Dr. Dowell, do you mind backing up just about a page?
Okay, 2 minutes. Okay, I'll be happy to do that. And please, when that happens, please let me know, because we're learning on this, and I don't want to be talking into a vacuum. So thank you for telling us that. Okay, let me back up. Let me back up a bit. I had started talking about deriving a single equation for the velocity potential. Did people hear that part? Are you with me there?
Yes, we heard that part.
Okay, fine. Let me just briefly summarize. This is the conservation of mass equation slightly rewritten. And as I mentioned before, we're going to talk about irrotational flow. And the way we're going to do that is we're going to say, let the velocity, fluid velocity Q bar be the gradient of a potential, the velocity potential. And we're going to try to derive a single equation for that velocity potential using this equation and also using the relationship between pressure and density. And so, for example, this term using Leibniz rule can be written in this way, where A squared is defined to be this speed of sound. And then moving along and evaluating the other terms, eventually we end up with a single equation, apparently a single equation for the velocity potential phi, which is this one. Okay? Are you still with me?
Yes.
Good. Okay. Now, this is not yet what I will call a useful form of the equation, or at least the most classically useful form, but it's an interesting equation all by itself. First of all, it is, we have to talk about the speed of sound squared in a moment, but as it stands, if I knew the speed of sound, this is a single equation for the velocity potential. It's a nonlinear partial difference equation. Here's the Laplacian of phi. Here's a time derivative. Here are some nonlinear terms. And as you may have missed, but let me say it again, when people first started doing computational fluid dynamics and solving the equations of fluid flow using what was then thought to be a revolution in computer technology, this is the equation they solved first. This is before they tried to solve the Euler equation, before they tried to solve the Navier-Stokes equation, which circa 1970 or thereabout, when the computer revolution really took off, this was the equation that one could solve with the computer technology of that day. And this equation is still solved by some people in certain contexts, particularly in nonlinear acoustics, for those of you who are interested in acoustics. But we want to also simplify this equation further, if we can, and still get a reasonably accurate answer. And so let's talk a little bit more about that. Also, I should tell you that this equation as it stands is not strictly speaking one equation for one unknown, because there are really two unknowns. One is the velocity potential, and the other one is the speed of sound. But the speed of sound can be related to, I think I found one. Oh, I should tell you that there's a typo there. What should that be, by the way? It's a to the z
squared.
Yeah, z should be equal to 2. So I found one of your homework typos for you. So anyway, the speed of sound is related to the pressure through this derivative, which if you use the state equation is just gamma p over rho, where gamma is the ratio of specific heats. For air, it's a constant equal to 1.4. For freon, it's 1.1. For freon is interesting because there are wind tunnels that use freon. And then, so I can either write the equations of fluid mechanics in terms of speed of sound or in terms of pressure and density, or any two of the three. But this gives a relationship among those three variables. So using this relationship and Bernoulli's equation, which we talked about a moment ago, one can finally obtain this relationship, which is essentially Bernoulli's equation again, but now it's written in terms of the speed of sound rather than pressure, right? And what I was saying, I hope, and we want to emphasize this point, the subscript infinity means I'm talking about a condition in the fluid which is far from the wing, where the fluid is not moving, essentially. I mean, I'm so far away, I don't even know the wing is there. So A infinity is the speed of sound when there's no wing, essentially when the air is just quiescent. And within the framework of small motions of the wing, one can essentially show that the right-hand side will vanish, and therefore A is equal to A infinity. And then if we go back up here, this is then a single equation for a single unknown, as advertised. Okay, but then we can do even better than that. Well, let me go back up here before I get into the small perturbation theory per se. If I now look at this equation and I think of A as being a constant equal to its value far removed from the wing, then it is a nonlinear PDE because of this term and this term. But if I am thinking of small enough motions, maybe the nonlinear terms are small compared to the linear terms. That's the idea of a small perturbation. And therefore, if I neglected this term and neglected this term and just had this term 1 over the speed of sound squared and this term equal to 0, that's a famous equation, right? It's a famous equation that you've studied in your course on partial difference equations. And that equation has a name. along with the other two famous equations you study in the first course in partial difference equations. And the name is, tell me?
The wave equation?
Wave equation, fine. And note that if I go further and neglect this term, and it's just del squared phi equals 0, that's also a famous equation. That is the, what's the other equation you study in your PDE course? Another famous person's name. You should never forget this famous French person.
The Laplace equation.
The Laplace. And then you also study the heat conduction equation, or sometimes it's, mathematicians, rather than using those names, sometimes talk about hyperbolic equations, that's the wave equation, elliptic equations, that's the Laplace equation, and the parabolic equation, that's the heat conduction equation. It will turn out, although it may not be obvious from this equation, that this one equation has all three properties. It will turn out to essentially be the wave equation when the flow is unsteady, but when it's steady, it will be the wave equation in supersonic flow and the elliptic equation or the Laplace equation in subsonic flow. And in between in transonic flow, which is the hardest case, it looks sort of like, but not exactly like, the heat conduction equation. Okay, so we're going to be trying to solve Laplace's equation or the wave equation and all those famous equations you studied in your PDE course. So now's the time when all those things you learned in the PDE course are going to become useful, if not before. Okay, so now the next, we're up to page 180. The next piece of it is we're going to do small perturbation theory. But when you do any kind of a perturbation theory, which is a powerful tool, by the way, in lots of engineering and science, including this subject, the first question is, I'm going to perturb, but I have to perturb about some reference condition, right? And depending on, and there are several possibilities of the reference condition. In the classical theory, we're going to perturb about a flow field, which is just a uniform flow field moving with a constant velocity, u infinity, and we're assuming that the motion and the shape of this slenderness, if you will, of this wing is so small that the dominant part of the flow field is just that constant velocity. And any change from that constant velocity flow condition due to either the shape of the airfoil or due to its motion is a small perturbation from that constant velocity flow field, okay? So, in small perturbation theory, we're going to assume all of these things. We're going to assume that the speed of sound is A infinity plus a perturbation. The pressure is the pressure at infinity plus a perturbation. The density, similarly, and the velocity vector is u infinity times I bar, where I bar is the unit vector in the flow direction, the main flow direction. So that's a big number, that's a big velocity, plus a small perturbation. And then if that's true, then the velocity potential, when I take the gradient of it, that is Q. So that's equal to this. And then this is the gradient of the perturbation of the velocity potential. So we're really going to end up with an equation for the perturbation to the velocity potential. The total velocity potential is u infinity times x. That comes from just integrating this equation with respect to x, plus the perturbation velocity potential, right? So this is a big number, this is a small number, but that small number gives me, to a small perturbation approximation, all the information about the pressure distribution on the airfoil due to its motion, the lift, the moment, all those other wonderful things we want to know, right? So finding that perturbation velocity potential is the object of our game. So first thing we need to do, is find the equation that governs that perturbation of the loss potential. And to do that, we're going to go back to our big nonlinear equation for the total velocity potential and then perturb it. Are you still with me? Are you still there?
Yes.
Yes. Yes.
Yes.
Okay. All right. Now, feel free to chime in and ask questions or dispute anything I've said. Okay. All right. Now, so what do we do? Well, here's our equation. We're going to look at each of these terms and evaluate them using this idea of a small perturbation. The first term is easy enough because, well, we'll see what happens in a moment. The linear terms are really easy. It's the nonlinear terms that require a little manipulation. So, for example, if I take del squared of phi, it's just del squared of the potential, excuse me, of the perturbation, because the first term in phi, first term in phi is just this term, but if I take two derivatives of that term with respect to x, y, or z, we're still in 3 dimensions now, then this term will go away. When I take the Laplacian of this, the Laplacian of the total potential is just the Laplacian of perturbation because the Laplacian of this is 0, okay? Same thing will happen when I take a time derivative. If I take 2 time derivatives of this, of course, these are just constants. They don't depend on time. X is not a constant, but it certainly doesn't depend on time. So when I take a time derivative of this term, it vanishes, and therefore this time derivative of phi is the same as the time derivative of phi hat. So those are easy enough. But now the second term, second term is a little more complicated. And now I see this. Yeah. Well, when I said second term, it's really all the other terms. So now I'm going to put in, I'm going to replace phi by a perturbation potential. So I'm going to have what? This term is still going to be the same. This term, yeah. This term, remember what I have del phi. I have this, right? And then I take that, oops, all right, went the wrong way. Take that and square it. And when I take the derivative of this, since I have a square, it's really del phi times 2 times the time derivative of del phi. You see that? Here's where I need my whiteboard, Michael. But if I take the time derivative of something that's squared, I get twice that thing times the derivative of that thing, and this is del phi, right? This term is del phi, and this term is del phi. Okay, so that's where that goes to that, and then I have this from here, and then here again I put del phi. This is del phi, then dotted into del of del phi dotted del phi, and I've just expanded that out. And then if I consistently neglect terms which are other than linear, that is terms of order phi squared, I get this. Okay. It isn't quite the wave equation as you may have known it, but it's almost, and we'll see what happens in a moment if I take all of this and combine it with this and put it back into that equation. It's that. Now, if I didn't have these terms, it would be, if these terms were not there, this would be just a wave equation. So why do I have these two terms? I have these two terms because of the coordinate system I'm in. I'm thinking I'm on the airfoil, and the fluid is coming at me with a velocity u infinity, and the fluid then gets disturbed in the neighborhood of the airfoil because the airfoil is there either moving or has a certain thickness. Had I been in a coordinate system not fixed with the wing, but fixed with the fluid, these terms would not appear. So another way to derive this equation, particularly if I were an acousticians, how many people took Professor Bliss's course in acoustics? Anyone take his course in acoustics?
Yes,
Anyone?
I did.
Okay, so you studied the wave equation a lot in acoustics, right?
Very much so.
Yeah. Well, unstable dynamics in the linear theory is just acoustics plus convection. By convection, I mean now this body is not stationary. In acoustics, the body is stationary and vibrates in some way and it generates sound, right? It generates pressure perturbations. But in unstable dynamics, the body has a overall large motion, in this case with a velocity u infinity. And so the body has a large motion u infinity, but then it's oscillating about that with a smaller motion. And that means that the wave equation in the coordinate system fixed with respect to the body looks like this. But if I were fixed in the fluid, it would look like the usual wave equation. So you might say, well, if that's true, why in the world would I want to use the equation fixed with respect to the body when the equation is simpler if I'm fixed in the fluid? You would ask that question, right? That's a good question. You were about to ask that question, right? Yes?
Yes.
Yes, very good. So the answer is, now you ask the question, what's the answer? Why would I want to be in a body fixed coordinate system, a wing fixed coordinate system with a more complicated equation when I could be in the fluid fixed coordinate system with a simpler equation? And the answer is I want to apply some boundary conditions on the wing, because I need to, when I solve this equation, I need to apply some boundary conditions. And it's much easier to apply the boundary conditions if I'm in a coordinate system fixed with respect to the body. And so I'm willing to pay the price of dealing with a slightly more complicated or maybe substantially more complicated equation for the overall PDE, because I'm gaining something by doing that. I'm gaining a simplification of how I apply the boundary conditions. In fact, there's an analytical solution to the wave equation, a formal analytical solution. Unfortunately, it's not useful usually because you can't apply the boundary conditions very readily. But formally, you can write down the most general form of the solution to the wave equation. But we're not going to use that method because it turns out not to be particularly useful. Anyway, this equation, 4.1.24, is the classical equation of linear small perturbation potential flow aerodynamics. And that's what's in most computer codes that the aerospace companies and NASA and all these other fine folks, Air Force, use most of the time. Even it requires, we'll see, a certain amount of numerical computation. In fact, the first heavy-duty use of computers in unstable aerodynamics was just used to solve this equation, quite aside from the nonlinear form of it. And there are a number of companies that will be happy to sell you a computer code that will solve this equation very efficiently. And we'll talk about what's in those codes or what is inside those models. So we're going to solve this equation subject to some boundary conditions. And as I mentioned, and also you can linearize Bernoulli's equation using small per item. small perturbation height is. That's this equation, 4.1.26. And so this equation tells me what the perturbation and pressure is given the perturbation of loss potential. So I'm going to solve, I hope, I'm going to solve this equation subject to some boundary conditions. Once I do that, I use that solution for phi to find the pressure, which is what I usually want, and then I'm done. As I mentioned a moment ago, you can reduce this to classical acoustics, and that's just a coordinate transformation from a fluid fixed coordinate system to a body fixed coordinate system or vice versa. And I'll let you walk through that. And that reduces the wave equation back to its acoustic form. Where now T prime is a T prime and T, the two times are the same, but the x's are slightly different. All right, T prime is still T, Z prime is still Z, Y prime is still Y, but X prime, which is the fluid fixed X coordinate, is related to the body fixed coordinate X in time through this transformation. This is usually called a Galilean transformation. I'm not sure why Galileo gets credit for it, but that's the name that's usually used. Okay. This is the general solution of the wave equation, where alpha, beta, epsilon. This is written in the fluid fixed coordinate system, where alpha, beta, and epsilon are arbitrary, except that they have to bear this relationship. The sum of the squares must be equal to 1. Well, you would think, well, that's the general solution. What's the problem? The problem is it's almost too general. There's so many possibilities for alpha, beta, and epsilon that finding combinations that satisfy the boundary conditions is not a practical thing to do. So we're not going to do that. We do need to talk about the body boundary conditions. And I'm going to give you a little bit of a preview on that. Think of some function f, which describes where the body is at any instant in time. And we'll describe where the body is with a vector r bar that's xi bar plus yj bar plus zk bar, where ij and k are unit vectors, x, y, z are a point where a body is in the fluid. And then you can also, and so the body position at some instant in time t is given by some function f r bar comma t is 0. But then if I think of the body moving to some other position, r bar plus delta r bar at some later time t plus delta t, that's got to be 0 too. And therefore, if this is 0 and this is 0, then the difference also has to be 0. That's the difference in f. But then using classical calculus, I can write that difference as the gradient of f with respect to x times a small change in x, y, and z, and also t, which in vector notation I can write in this. And thus, this gives me a statement about the body and its motion in terms of geometry, if you will. And then if you remember your calculus, the normal to a surface f, any surface f, is the gradient of f divided by its magnitude. That's a unit normal. Without the division, it would just be a normal vector of some magnitude. But we like n bar to be a unit normal. So we do that. And then we actually have to think of a little physics. Here's a picture. Oh, I have a picture here, so I have to draw this. This is the same thing, but now depicted in graphical form. So here's where the body was at some time t. Here's where it is at a later time t plus delta t. And then you can see the change in r bar. That's the vector that gives me scalar components x, y, and z. And then I say, but velocity of the body, the vector velocity of the body, is just a small change in r bar divided by a small change in time, and the limit is delta t goes to 0. That's what Newton said we should think about in calculus. But then the normal velocity to the body is v bar dotted in, so it's this thing. So this is the normal velocity of the body. Okay, this is just geometry, vector geometry. But we want to say that the normal velocity of the body, which is this thing, and then using one of the earlier equations, I can write this in this form. The normal velocity of the body must be equal to the normal velocity of the fluid, assuming that the fluid doesn't penetrate the body. I'm assuming I have a solid body and the fluid has to stop. And I'm only dealing with the normal velocity because I have an implicit theory which ignores viscosity, which means I can't think of, I cannot say anything about the velocity tangential to the surface. I can only say something about it normal to the surface. But if I take all of this together, then this, in fact, is the general normal to the surface boundary condition. It relates F, which tells me what the body is doing, to the velocity of the fluid. And of course, on the body surface, F equals 0 by definition. But then I can simplify this for the cases that are usually of interest to us. In general, I have a function f, x, y, z, and t equal to 0, but I can also write this as, I can think of z, which is essentially the coordinate normal to the wing, right? Normal to the wing. I can say that's given by some function x, y, and t. And that function x, y, and t tells me how what the wing shape is or how it moves in time. It tells me everything I need to know about where that wing is. And then if I rewrite this equation in terms of the little f, I get the form that is useful and helpful to us. So here's my picture of an airfoil. I made it fat so you can see what I'm talking about. ZU is the position of the upper surface at some position X and also Y. Z sub L is the position of the lower surface. And where the upper surface is and where the lower surface is depends on the shape of the airfoil, but also depends on how it's moving. And then if I linearize that boundary condition in a small perturbation sense, well, first of all, I can rewrite it in this form as still in a nonlinear form, but now written in terms of small f. So this is the equation that must be obeyed. U is the fluid velocity in the x direction due to the perturbation. And in linear theory, I'm going to neglect that and only retain this because this U is much smaller than this capital U. This is also a nonlinear term, as is this small u times this. So in the linear theory, I'm going to neglect this term and also this times this. But then this is equal to the velocity, fluid velocity component in the z direction. And this must be true on z equals small f. But if f is truly small because the body is thin, slender, and if it's not moving very much, then rather than satisfying this boundary condition on z equals small f, I'll just satisfy it on z equals 0 and hope that that's a reasonable approximation. In fact, you can show to a consistent order, doing that is consistent with neglecting these nonlinear terms. So, finally, we have the body boundary condition. F, small f, is a given quantity. From the aerodynamicist perspective, F is given, right? Someone told the aerodynamicist what the motion was. And then that tells me what the vertical velocity of the fluid component is on z equals 0. So this is not the only boundary condition we're going to have to deal with, but it's the most important one. So we're going to use this boundary condition plus a few others and solve the wave equation. And now we're almost at the end of the class. So the next thing we're going to do, and you're going to read about this, I hope, before we do it on Thursday. The next thing we're going to do is we're going to take this wave equation, this boundary condition, and do a two-dimensional supersonic flow calculation for an oscillating body. Again, the basic formulation I've gone through today is valid for three-dimensional as well as two-dimensional flow, and we are going to talk about three-dimensional flow, but we're going to start out with two-dimensional supersonic flow because it's the easiest one to deal with. Then we'll go to 3 dimensions in supersonic flow. Then we'll go back to subsonic flow, which is harder, but we won't bother to do two-dimensional subsonic flow. We'll go right to three-dimensional subsonic flow. And then we'll talk about why this all falls apart, why small perturbation theory falls apart when we get near Mach 1, near the transonic condition, and discuss what to do about that. Okay. I've left a few minutes for questions. Questions? Protests? Objections? Applause is also in order. Any questions?
Thank you again, everyone, for participating remotely. Again, we're still working the kinks out of the system, so thank you for your flexibility. We will continue to meet through Zoom. The exact details of what you see on the screen are what's going to change. This meeting number is going to be used for the rest of the semester.
Thank you, Michael. Thank you, everyone.
Thank you.
Thank you, Professor. Have a nice day.
Thanks, Professor.